So this session is the continuation of last session, that is Faraday's law of electromagnetic induction. In the last session we have seen that what happens if a magnet is moved towards and away from a coil. We observed that the galvanometer showed some deflection, and this is called as electromagnetic induction, and this is due to change in flux linking the coil. Now, and also we have noted down that the speed of the magnet determines how much current is produced. So if the speed was more, a greater current is induced, and if the speed is less, there is a less EMF induced. All these points can be put together into two laws. Faraday's laws of electromagnetic induction. There are two laws. First, we'll write what is first law. The first law says that whenever the flux linking a coil or circuit changes, an EMF is induced in it. Whenever the flux linking a coil changes, an EMF is induced in it. An EMF is induced in it, and the induced EMF is directly proportional to the rate of change of flux linkage. This we have seen that when the coil is moved towards the coil with a greater speed, or if the speed is increased, the deflection increases. That means that the induced EMF depends upon the rate of change of flux linking the coil. That we can put here as second law. The magnitude of the induced EMF the magnitude of the induced EMF in a coil is directly proportional to the rate of change of flux linkages. Directly proportional to the rate of change of flux linkage. Now, the two laws can be together written as if E is the induced EMF in the coil, then E is directly proportional to d phi by dt. This is what Faraday's law says. Whenever the flux linking the coil changes, an EMF is induced, and the EMF induced is directly proportional to the rate of change of flux linking the coil. Now, what about the direction? When we did the experiment, we have also observed that when the magnet is moved towards the coil, the deflection is towards one side, and when the magnet is moved away from the coil, the deflection reverses. That means it is to the other side. If in the first case it was towards right, in the second case it was towards the left. So how can we determine the direction? The direction can be determined using Lenz's law. Lenz's law gives the direction. So first I will write the statement, then let us understand what exactly is this. So the Lenz's law states that induced current in a circuit, or induced EMF, induced current in a circuit or in the coil, always flows in such a direction that flows in such a direction that it opposes the changes in magnetic flux linked with circuit. It opposes the changes in magnetic flux. It opposes the changes in magnetic flux linked with circuit. Or the very cause that has produced it. What is the meaning of this? Now, it opposes the very cause producing it. Therefore, it opposes. So, the equation for E is now becomes, if there are n number of turns in the coil, then it can be written as the induced EMF is n into d phi by dt, and according to the Lenz's law, it opposes the very cause of producing it. Therefore, this negative sign will appear. The negative sign indicates the opposing nature of induced EMF. Minus sign indicates the opposing nature of induced EMF. Opposing nature of induced EMF. And now let me explain what exactly is this. How can we determine the direction of induced current? Now let us say that we have a coil over here and a magnet is moved towards the coil with north pole here and south pole on the opposite side. Now the north pole is moved towards the coil. The magnet, so this is the coil or a circular loop. The magnet with north pole is moved towards the coil as shown in this figure. Now according to the Lenz's law, the induced current should oppose the very cause producing it. Now what is the cause producing? The induced current is produced due to the motion of the magnet towards the coil, and it is due to north pole moving towards the coil. Now the induced current in the coil should oppose the motion of the magnet. So the north pole is coming towards the coil. The coil should now say, "Hey north pole, you do not come, you go away from me." It is possible only if this side of the coil acts as a north pole. To get a north pole, the induced EMF should be in the anti-clockwise direction. Now it is very clear that when the magnet is moved near to the closed loop with the north pole towards the loop, the current produced should be in such a direction that a north pole is induced on this side of the loop. And to get a north pole, the current must be flowing in the anti-clockwise direction. So this is how we can determine the direction of the current using Lenz's law. On the other side, if we have a coil and if the same magnet is moved away from the coil, now we have north here, south here, and let us say that the magnet is now moved away from the coil. Now what happens? Now north pole is moving away from the coil. So the coil must say, "Hey north pole, don't go away from me." So it is possible only if this side of the coil is as a south pole. That means south and north will attract each other, or it will oppose the motion of the magnet away from it. Now a south pole is possible only if the current flows in the clockwise direction. Therefore, when a north pole is moved away from the coil, a south pole is produced in such a way that the induced current flows in the clockwise direction. So, by this it is very clear that when the north pole is moving towards the coil, to oppose this motion, an anticlockwise current is set up in the coil. And when north pole is moving away from the coil, to oppose this motion, clockwise current is set up in the coil. A clockwise current produces south pole, and south pole can attract north pole. The south pole produced in the coil attracts the bar magnet, and hence it opposes the motion of the magnet away from the coil. This is how, using Lenz's law, we can find out the direction of the induced EMF. We can do some more problems based on this to find out the direction of the induced EMF or the induced current. So, using Faraday's law and the Lenz's law, finally the induced EMF is written as E is minus N into d phi by dt, where E is the induced EMF in the coil and N is the number of turns in the coil, and d phi by dt is the rate of change of flux linking the coil. Rate of change of flux linking the coil. And negative sign indicates the opposing nature of induced EMF or induced current. Minus sign indicates the opposing nature of induced EMF. And this is very, very important, how to find out the direction of induced current, because in the exam you will be given a circuit and they will ask you whether a north or south pole is induced, or they will ask you to write down the direction of current or induced EMF. So, this can be done using Lenz's law, and it is very clear. The current induced is in such a way that it opposes the very cause which is producing it. Here in the first case, the cause for the current is the motion of the magnet towards the coil. So, to oppose it, it will set up a current in the anticlockwise direction. And in the second case, the induced current is due to the motion of the magnet away from the coil. To oppose it, this motion, the coil sets up a current in the clockwise direction. Hope this is very clear.